Hello everyone, welcome to today's discussion session. Today is the week 5 of our discussion of this course, which is Coherence and Quantum Entanglement, and we will start in few minutes. Let us wait for few minutes to so that the participants join. So let us wait for that, and I will start formally within 2 minutes. Okay, so let us start today's session. So today I welcome back you all of again for the week 5 discussion for this course, Coherence and Quantum Entanglement by NPTEL. this by now every one of you know me who and the instructor also, so I'll not go through all of this again, but welcome back again for today's discussion. So today we are going to discuss about second order polarization coherence theory, coherent mode representation, and also review of quantum mechanics and quantum mechanical correlation functions. So for these, for these parts, whatever I have written here, those are already discussed and in very elaborative manner in your lectures, but today we are going to solve the questions related to the whatever the assignments going on for week 5 and week 4, as well as we'll learn about this concept again. If you have any doubts, questions in your mind, you can ask me, because in week 6 and so on, week 7, you will get the questions from polarization coherence theory, coherent mode representation, review of quantum mechanics and quantum mechanical correlation function. And apart from that, also today we are going to discuss about some problems from special degree of freedom, some from angular degree of freedom. And before that, I will show the homework problem that I gave, the two last part of one question as homework. I will discuss them. So those are the questions part, and apart from that, of course, as we discuss the theory again in this discussion session, I will do so in this class also for these 4 topics. And by now I think you guys have enough background of coherence theory in all of the degrees of freedom, like temporal, spatial, angular, and what is orbital angular momentum of light, as well as we'll learn now about the polarization coherence theory also. So this was your homework problem, like not home 50% of it I solved in the previous class, and last two part I think I gave you as homework problem. So I hope everybody of you have done this. If not, I will go through this once again very quickly, and because I am focusing on these questions, these problems, some questions I have focused very much, because those kind of questions are which those kind of questions you can expect in your examinations also. And of course, you will see that the questions which I used to solve, those are very much related to the assignments or quizzes what you get, and maybe sometimes directly from the assignments also. I try not to do those kind of problems directly in this discussion session, such that you guys give your own effort to solve the problems, but still some part of it you can find here, and some part of it, if you are not getting here, then you can again expect those in end sem and end sem kind of like the final examination also. All right, so this was the question. Let me go through this once again, and or maybe wait for 3 minutes more while other people are joining at 5 p.m. In between that, I will mention about the I'll mention about the Google Drive folder, as well as the YouTube link where you can find this, because these are the key points which I used to tell you on every class at the ending and at the beginning and the ending, because those are the necessary stuffs that you need on the daily basis to study by yourself. So so this is the drive folder link. Once again, I am sharing. I use like the other classes, and this is the YouTube channel link where you can get the videos. So I hope everybody of you have there was some mismatch in the timing for the previous week. That's why it was shifted to, like, some problem was there from my side. That's why it was shifted to Sunday 9 to 11 a.m. Maybe because of that somebody can miss that class, as it was not on the regular time and regular day. But I hope if you have missed that class, then you can visit to YouTube channel, I mean YouTube video link, as well as the drive folder link. Everything is uploaded there. And anything you need to ask, you can comment down below, or here you can ask, or in the YouTube chat section, or mail me in my mail ID. Let me many people used to mail if for books, or some question. Mostly people ask for some references, so you can also, you guys can also mail me if you require anything. Alright, so I'll start from the previous day's last question, which we are solving, and on Sunday, and we'll start from here, and then we'll go. My plan is today, for after doing this, my plan is to discuss about this second order polarization coherence theory, then coherent mode representation, review of quantum mechanics, and quantum mechanical correlation function. And you can see whatever problem. I mean, I will solve some problem from the special degree of freedom today, and some from the angular degree of freedom. I will not probably do anything from polarization degree of freedom, the, I mean, problems part, but that will be for next week. And I am trying to go with the time by time with the assignments, such that no assignment problem is solved directly by me in the discussion session, but sometimes some part of it you can find in these sessions also. And of course you can discuss with me about your assignments problems, and anything, any problem you need to discuss. All right, so let me so it is already 5:01, so let us start discussing the problem. So the problem was telling that coherence, for this it is a spatial coherence mainly. A spatial coherence is a requirement for measuring multiple intensity interferograms in this figure, in this Mach-Zehnder interferometer, where whatever it is showing over here. Now, however, the scheme in the figure below can do so through measuring only one intensity interferogram. Consider a spatially partially coherent field of frequency omega 0 incident onto the interferometer. The travel time of the on the interferometer, and then the travel time of the field in the two arms of the interferometer is T1 and T2. The wavefront inverter consists of two lenses of focal length f placed with separation 2f between them. Ignore any divergence from the of the field, and take the proportions of the field reaching the detector through the two arms to be K1 and K2, such that K1 part is going in this side and K2 in this arm 2. Now this is the scenario given to you, and this is an inverter, the combination of lengths which is inverting the field, that you need to consider for this path 2 or arm 2 only. Now based on these, you are asked for few questions. Now you need to solve this. I already started to solve this question in the previous class, but not solved totally. And I told that in the next class, that means in today's class, I'll solve this very quickly. In between that, you try to understand understand this question, as well as do it by yourself. Already I showed some part of it, like A and B, to you. So today I will not elaborate or explain this question in very detail again. If you require that explanation again, then you can go to your week 5 YouTube video in the YouTube to find what we discussed. Not much, and I hope everybody of you at this moment are aware about the fact that how to write E input, and how to write E output in terms of E input. That is the main thing that you need to learn in case of doing anything with the interferometers. And once and then you know E star E is the intensity that you need to find for the intensity, to get the intensity form of the intensity. These are very straightforward, I mean, these are very repetitive questions I find. All of the things we are doing, sometimes in temporal, sometimes in spatial, sometimes we will do in angular and polarization, but the process is I mean same, but you need to be very cautious and careful about calculation because it is very tedious solution. These solutions are mostly tedious, and you need to use the gamma function integration and all those integral I have mentioned several times, the some special integral, some Gaussian function integral. Those if you remember, then it will be easy to solve these problems. Otherwise these are very straightforward. So the first question, it is telling that write down the field E output at the output port of the interferometer in terms of input field and other experimental parameters as mentioned above. Second, it is telling about the find out the intensity at the output port of the interferometer in terms of the input field intensity I in rho and other experimental parameters as mentioned above. So these two, as I have already I already solved these in the previous class, but let me write it very quickly. E output will be some k1 E input rho e to the power minus I omega 0 t1 plus k2 times E input. Now it is inverted because it is mentioned in the problem, and I omega 0 t2, and t1 and t2 it is already mentioned in the problem again. Now part B, it is I output rho, which is like azimuth, the average, or like ensemble average, and E star out rho E out rho, it will become k1 square E in star rho E in rho. Sorry, my handwriting is becoming poor, so let me write it slowly. Then k2 square average E in star minus rho E input star in input minus rho plus k1 star k2 E in star minus rho E in rho e to the power I delta. Sorry, e to the power minus I delta. If it is plus minus, like whatever you can write actually, just two complex conjugate two complex conjugate things, minus I delta plus k1 k2 star E in star minus rho E in rho to the power I delta, which is again equal to k1 square I in rho plus k2 square I in minus rho plus k1 star k2 w rho minus rho e to the power minus I delta plus k2 star k1 w minus rho e to the power minus I delta, where delta equal to omega 0 t2 minus t1, that is the path difference itself. So now these two parts I have already done in the previous class, but this is just to remember you and be habituated again and again with the solution process. That's why I did again. So now let us move towards C. It is saying assume that the incident field is spatially stationary. How does the expression for I out rho simplify? So if the field is stationary, we have w rho minus rho equal to w, I mean it will just become a function of w delta rho. So what is delta rho? Delta rho is nothing but rho 2 minus rho 1 minus rho 2 or rho 2 minus rho 1, whatever in terms of, like it is mod, it does not matter. So you can take this rho 2 minus rho 1. Now one is rho minus of another is minus rho, which will give you 2 rho. So now it is w 2 rho, and I input rho is now w rho, which is equal to w0 equal to I0, where I0 is the constant intensity of the incident field. So therefore, I mean, that means it's nothing but that the first two term of this, like these two terms, this I in row and I in minus row, those will become constant, and now we can write it like I out row equal to k1 square I0 plus k2 square I0 plus k1 star k2 w2 rho e to the power minus I delta plus k2 star k1 w2 rho e to the power I delta. I am sorry, this environment is a bit noisy because I am not in my institute at this moment. I am outside, so sorry for the inconvenience if you are getting noise from my side. Please bear with me for this session. From upcoming session we will be again from I will be again in my institute, so there will be no such issue. Okay, so this will become I output for the stationary, especially stationary field. Okay, and now the problem D part, it is telling that now assume that the cross spectral density of the field is both stationary and real. Taking k1 k2 equal to half, so how the cross spectral density could be measured by you measuring just one intensity interferogram. So for that, let me solve. I have already given you this as a problem, homework problem. I hope you have understood what it is telling, that you just need to take one interferogram, like that means this is one shot measurement, just you will measure once, and you need to have the idea, measurement or the like information about the cross spectral density, and how will you do that if k1 equal to k2 equal to half. So for that, what we need to now what we will do is as follows. I am not explaining whole of the scenario again. Whoever has joined, please, first part you can see from the YouTube channel, like video, and this part, just whatever I am doing, just follow that, and read the question to understand that what I am doing. Okay, so k1 equal to k2 equal to half. So now I output will become I output rho is equal to I0 by 2 plus 1 by 4. Now I am writing the W in terms of like its real part and imaginary part. Okay, and we'll have two of this part, because one for this and one for its complex conjugate. I am sorry if it is half I0 by k1 is equal to I mean, I hope you have understood how it is coming I0 by 2. Let me write k1 square means 1 by 4, k2 square means 1 by 4, 1 by 4 plus 1 by 4 means I0 by 2, and now it is 1 by 4 k1 star k2, and we real part of w2 rho plus I imaginary part of w2 rho, and e to the power I minus I delta, we can write it as it cos delta uh, let me for the first part it will be minus I sin delta, and the next part it will become 1 by 4 real part w2 rho plus I imaginary part w2 rho. I hope this is very clear to you that cross spectral density is a complex quantity. It is not an imaginary quantity, and from the beginning of this, no matter it was temporal, spatial, angular, whatever, we are very much clear about this thing, that W is playing the main role, that means cross spectral density or the cross correlation function, maybe it is in whatever degree of freedom this is what actually, and the e to the power I delta, the phase adding due to the path difference, these two parts are actually creating the are the cause of interference that we observe. And this is not a real quantity, this is an imaginary quantity. And imaginary I mean, this is not imaginary, I am very sorry, like this is a complex quantity, it will have some real part, some imaginary part. And from we learned how to calculate visibility also. We have seen that this visibility directly depends upon W, which means it directly depends upon the degree of coherence. So degree of coherence mu or W, these things are complex quantity, and we are writing that's why we are writing it in terms of real and imaginary parts. So now it is mentioned for this case, this question, that this is stationary. First of all, stationary, and the field is real. I hope you can understand that it is told that assume that the cross spectral density of the field is both stationary and real. This is conditional. Like in one class somebody of you were asking that why we are using always like this, why we are not it can be stationary, it can be real also, this that with various conditions. So these are the conditions, the conditional questions where you had given with some conditions, and for that particular condition you need to find out the problem. For the theoretical part, whatever we have learned till in the theory manner, those were the generalized theory that you can that will help to learn. Now the conditions you need to apply according to your problem given to given I mean problem given to you. So based on this, it is stationary and real, so we will have imaginary of W2 rho as 0. So I output rho will become I0 by 2 plus 1 by 2 real of W2 rho. I hope you have understood why it becomes imaginary of 2 rho becomes 0. Okay, and this thing I discussed in the previous class also. This is just a recap of the previous class, because I discussed this part and I told you to solve as homework problem. So now if we keep this delta, then this delta can be n pi, that where n equal to 0, plus minus 1, plus minus 2, etc. So for any n pi, like if it is 0 pi or 1 pi, 2 pi, 3 pi, anything, what we'll get is w real of W2 rho equal to 2 output rho minus I0. That means if you measure this I output rho just one shot, and you have this information of the field I0, so if you just do 2 I output minus I0 with the one interferogram, you can get the real part of the W rho, the information of that. That means by measuring just one intensity interferogram I output rho, and knowing the input intensity I0, this is the input, one can measure the cross spectral density function of the field. Okay, so this kind of problem you can expect in various form, like in quiz assignments or NSEM. Now the thing is that from this one thing you can understood that you can understand that this has some problem, like we are considering this as stationary field, as a real field, then only we can find it with only one shot. But if we need to and that's why we are only getting the real part of cross spectral density. But if you want to measure the imaginary part of the W2 rho, then it is not this interferogram I mean this process is not true. For that you need two shot measurement, and there are like various, like still now to do the to get whole information about the cross spectral density is itself a research problem. Like if you like how to retrieve the w, like the cross w means the cross spectral density, or like the cross correlation function in various degrees of any degree of freedom, to fully recover that, to fully get the information of w, is itself a research problem. And many a research has been carried forward by many groups, of course in Professor Ananja's group also. So if you want to have look, then you can find the research papers also, because if anybody of you have any interest, you can think in this direction also. So this was the first question, and the homework problem also that we wanted to discuss. Now I will start with the second order coherence theory for polarization. I hope this figure, I don't know, I forgot that if it was in the lecture or not. I hope it was there in the lecture. So this is just showing an interference setup for, this figure is showing just the interference setup for in polarization degree of freedom. How, that we will understand, but let us formally discuss this. So far we have studied only the scalar fields, like in which we are concerned with only the magnitude of the field, like maybe in spatial, in temporal, or maybe in angular. And you are very well known with this fact that light is a vector, and polarization actually gives gives us the feel, or polarization, study of polarization is a study, is the thing where we do the where we do consider light as vector field. So now we are going to study the vector field, and that means it has both magnitude and direction. The direction in which an optical field vibrates, that's called polarization. And here we are going to study about the polarization properties of light, and how to quantify electric field vibrations in one direction are correlated with the electric field vibration in some other direction. Do you understand what is uh, polarization coherence? If you ask this question, then to understand it, you can say this, or you can understand in this manner, that how electric field vibration in one direction are correlated with the electric field vibration in some other direction. That is what we quantify by using the coherence theory of polarization, or the degree of coherence in polarization. So we will treat polarization just as like we have treated in time, space, and angular position. So polarization is a two-dimensional vector. An optical field with its electric field vector oscillates in horizontal direction is called horizontally polarized field. Like in this direction, this is x polarized field or horizontally polarized field. Similarly, if a field is electric field vector is oscillating in vertical direction, it is called vertically polarized field or y polarized field. Excuse me. The vectorial electric field Et at time t and z equal to 0, then we can write it as E equal to Ex x cap plus Ey y cap. That means some part of it in the x direction and some part of it in the y direction. In terms of x and y, we can write in any directional vibration. Okay. Now as we are we will consider here only for the monochromatic case. For that frequency, whatever we will consider here, like whatever the phase we will add, that will be at particular for a particular monochromatic field. That's why we will consider just omega. You can if you don't consider that, then it will become much more difficult problem. But right now we don't need to do in that direction, and mostly whenever we are doing we are doing experiments also, then we consider we do with particular frequency only, so no need to worry about that here. And the amplitude, what I am talking, that Ex Ey some in the x direction and y direction, are itself the complex analytic signal corresponding to real random electric field amplitudes. Okay. And in situation, I mean there can be situation where x direction vibration and y direction vibration, which is making a total electric field, that x and y can be perfectly correlated, which we say perfectly coherent field in polarization degree of freedom, and it can be partial also and incoherent also. Maybe we can write it like whatever I am saying, let me write that. Like we can write electric field as a vector field now. Okay, now these ex and ey are, I mean for the case when ex and ey are mutually perfectly correlated, that represents perfectly coherent field in polarization degree of freedom. In situation where ext and uyt are not mutually perfectly correlated, then we can only do its symbolic representation, and in this situation one needs to know about the correlation functions. The four topics I have mentioned today, which we are going to understand, one is the polarization, second order polarization coherence theory. Second is the I mean let me go to the slide. First is the second order polarization coherence theory, then it is coherent mode representation, then it is review of quantum mechanics and quantum mechanical correlation function. Now the question is, we have already understood what are the correlation function, what is coherence for in various degrees of freedom, but when it comes for the but those are mostly for the scalar field. Now when you are considering vector field, there comes the concept of polarization, and we need to do it for that also. And there was one question in the ask a question portal I saw, that what do you mean by symbolic and non-symbolic. For that question, regarding to that question, I am saying that if we have ext and uyt which are not mutually perfectly correlated, then we can only represent electric field in symbolic manner. And in that situation one needs to study the relevant correlation function, without that is not non-symbolic. Okay, but I think none of whoever is present here in I don't think that you it was not a question from you guys. So whoever was there, maybe he can see see this discussion session later on, and get his answer. And if not, then if anybody else also have the question, then you can write again in the ask a question portal, or discuss, or whatever I have mentioned several times. Okay, so now I hope you guys have the idea that why we are worried about studying the second order polarization coherence theory in coherence theory also. So after that we want to study the coherent I mean the how to quantify the polarization correlation, and for that we need the help of a interferometer setup, like previously we have done for the Mach-Zehnder. We have used Mach-Zehnder mostly, but we have also I have also shown you how to do it with the Michelson interferometer. But if you considered an interference setup in this regarding for this polarization degree of freedom, then we need to take help of wave plate and polarizers. This is a simple setup, but this what depicts or perfectly mimics the setup of Mach-Zehnder interferometer. How and how is that so? I mean, how is it so, that I will discuss now. So you can see that this is z equal to 0 plane, this is z equal to z1 plane, and this is z equal to z2 plane, and we know how from now on how we will will we write the electric field, that is in terms of vectorial form, which is ext x cap plus eyt y cap. Excuse me 1 minute. And our motive is to know how the electric field vibration in these two directions are correlated. So so now at field z equal to z1, I hope you can see my screen. At z equal to z1, right after the passing through the wave plate, the field will become Et at z1 equal to Ex t z1 x cap plus Ey t z1 y cap. That means it will add some phase, because we know what is wavelet, what is polarizer. Now any one of you, if if you do not have the idea of how to represent this electric field in terms of tensor or matrix, then you need to, it will be very helpful if you learn that. That means you need to understand the Jones matrices of the optical optical elements, because these polarizer or wave plate or anything whatever we are saying here, those all can be represented in terms of matrix or tensor. So here I, because you know that as I am writing ETZ like this, so what we can write it as these also. This is just a column vector. So electric field is a can be represented with the column vector. And if you do not have idea or don't know how to use the Jones matrix, Muller matrices, and yeah, like you don't need to learn about Muller matrices, but the Jones calculus mainly, then you should go through once. If you have any doubt, you can ask. It is not compulsory that you need to understand everything of it, but now you can have the idea that how we can use or write electric field and do operations by using matrix formulas or Jones calculus. But the excuse me, so that will make your life easier to solve the problems for polarization degree of freedom. Let me wait for 1 minute. I am having very coughing. Okay, so all right, so that part you need to learn, and if you have any problem, then we can discuss it once in next class. If anybody of you mail me or ask me, then only, otherwise we'll move forward. Okay, so all right, so now we can write this extz1 as ext e to the power I epsilon e to the power I kz1, because for moving to some direction it will gain some phase which is I kz1 e to the power I kz1, and e to the power I epsilon 1 is just nothing but, as you can see here in this slide, that it has epsilon 1 and epsilon 2, and you know what is a wave plate, and we actually use birefringent materials for this kind of wave plate. So it will have, it will gather some it will acquire some phase as it will pass through as it will pass through the wave plate, and it will have different phase in different direction x and y, because it is a birefringent material. So now it is x cap plus we can write it as EYT e to the power I epsilon 2 e to the power I k z1 y cap. So where kz1 is a constant phase acquired due to the propagation by fields in both the direction, and epsilon and epsilon 2 are the phase that is given by particular wave plate in a controllable manner. Now the two fields are combined using a polarizer to study the interference effects, which you can see in the next next part, which is at z equal to z2 field. I mean z equal to z2 I mean this is a plane, sorry, z equal to z2 plane. So a polarizer of one kind passes that polarized light while blocks the other, and by using the concept of that, the polarizer of two x and y, we know how we can control the x portion and y portion through the wave plate and polarizer, and we can get to see the interference effect. So we now we take the polarizer to be oriented along direction x dash, which is at an angle theta with respect to x direction. For that, we can write x like cos theta x dash minus sin theta y dash, and x and y equal to sin theta x dash plus cos theta y dash. So why this? Because this is nothing but the coordinate transformation, and we know how to do coordinate transformation in r theta basis, that is the I mean sorry, in the theta basis or x dash y dash basis, not theta basis, I am sorry, like this is the xy. Now it is moving through y dash and x dash theta. Then what will be the x dash and y, what will be the x and y in terms of y x dash and y dash, or vice versa, what will be x dash and y dash in terms of x and y, that you can write like these two equations. So ETZ2 now becomes EXTZ2 x cap plus EYTZ2 y cap, which is ex dash t z2 x dash plus ey dash t z2 y dash, because now this is our coordinate and we need to write it in terms of like that theta, sin theta, cos theta, like we need to do this transformation. Okay, so for that, what will be the thing? It will be ext e to the power I epsilon 1 cos theta. Like, let me not directly write it, let me do the step by step thing. Let me do it step by step. So let me not write it this also. Let me do it step by step manner. So now just substitute x and y. EXTZ2, x means cos theta x dash minus sin theta y dash plus EYTZ2 y cap equal to sin theta x dash plus cos theta y dash. Okay, I hope you can understand this step what I have done. Now I am separating out x dash part and y dash part into two, and it will become now ext to the power I epsilon 1. I am writing epsilon 1 because I will directly write this thing also. Epsilon 1 cos theta plus EYT e to the power I epsilon 2 sin theta e to the power I k z2 x cap dash plus minus of ext e to the power minus e to the power I epsilon 1 sin theta plus EYT e e to the power I epsilon 2 cos theta e to the power I k z2 y dash. Okay, so this will become now the field at z2 plane. Now if you calculate, so this is the thing with x dash and this is the thing with y dash. Okay, now you have the polarizer, and suppose the polarizer is at 0 degree such that it is such that it allows to pass the x direction polarization part only, and it blocks the y direction, because polarizer, you know what is y plate, what is polarizer works as like it selects the particular polarization light and blocks other. So now we are considering that the field passes through the polarizer, and and we find the field that after passing through the polarizer how it superposed and what we get as interference or intensity. Okay, so for that if it passed through the if it passed through the horizontally polarized if the horizontally polarized light only passes, that means if we present a if we keep a polarizer which is passing only the x polarized light, then it will become like the field will become only this, because this will only pass. Now if you have the if you calculate the E star Ex star Ex, that means intensity, then what we will get is nothing but like we will get the intensity, of course. Then what we will get is nothing but the intensity, but now it is in polarization degrees of freedom, which will become nothing but, you can calculate it by yourself by step, just put this thing, the star part here and this part here, and write the step by step things. Then what we will get is this cos square theta plus ey star t eyt sin square theta plus ex star t eyt cos theta sin theta e to the power I epsilon 2 minus epsilon 1 plus complex conjugate part. Now the thing is that I hope everybody has understood what you need to do in case of polarization degree of freedom, because these all of the thing whatever I am telling at this moment is already covered in your lecture, but this is just to make you remember again and to make compare to understand it better, like why we are talking about polarization suddenly, which is not mentioned in the lecture clearly. So that's why I focused on this part, and again I showed you that in a similar manner like temporal, you can do calculate it for polarization also. And this is just showing that these two pictures I have shown here is corresponding to each other, like both of them are showing the interference. One is in the polarization, this first part, which is consisting of one wave plate and one polarizer only, whereas the second is showing the temporal interference, for which we use a Mach-Zehnder type interferometer. So this first dashed line is showing the z1 plane, from z equal to 0 plane, and the second dash line is showing z equal to 1 z1 plane, and this last output part is showing z equal to z2 plane. So now you just make the analogy that how we are depicting these or mimicking this in temporal interference in Mach-Zehnder interferometer into the polarization interference. But now Now we can similarly calculate the visibility and all of those. And you have already gone through all of the mathematics that were shown in your lectures, that finally you get a matrix which is called J matrix, and mostly whatever the Jones Forman matrix are, those are represented with J. And finally you got a visibility quantity, I mean a quantity which is visibility, which is directly depending on the determinant of that J and trace of that J. But whatever I am saying, if you do not have followed, if you have not followed that lecture notes, then it will be difficult. So I that's why I just started with the similar things which has already done in the lecture, but now I'll directly write the formula which are important for you in your examination. So I hope you have the idea why we are doing the polarization in we are doing the coherence theory in the polarization degree of freedom. So the formulas which we are going to use here, those are, let me write it, 1 minute. Those are visibility. These the questions from this polarization degrees of freedom has not covered yet in the is not covered yet in the assignments or quizzes. So be careful with this thing. Whatever I am telling, it will help you in your assignment quizzes and so on. You will certainly get 1 or 2 questions in your assignment from this formula. So this is the visibility, and where J is the matrix Jxx Jxy Jyx Jyy, and you know that determinant will be Jxx Jyy minus Jxy Jyx, and trace of J will be Jxx plus Jyy. And you all are aware how to find the determinant and I mean trace of the matrix. But what you need to know is this J matrix, which is the correlation matrix. Okay. You have also learned about completely unpolarized field, how to represent that in terms of J matrix, and how to represent polarization matrix also in terms of J. And the degree of polarization can be written in terms of P, which is directly equal to V, that is visibility. That is the beautiful thing here in polarization degree of freedom. I mean, not in the polarization degree of freedom, I mean in every degree of freedom. That's what we have observed. And this J, any J metric can be right in terms of polarized and in terms of the summation of polarized and unpolarized part, which is this, whereas this P is the degree of freedom and 1 minus P is the 1 minus degree of freedom. You will get one question from this also, I hope, I mean hopefully. But now the question is that before going to the questions, I mean the discussion on the finite dimensional basis and infinite dimensional basis and the coherent mode representation, I will give you one thing to do by yourself. That let me draw. Light is coming and falling on it, passing through it. Okay, so this is a quarter wave. This is a quarter wave plate. Let me write in full. Quarter wave plate at 45 degree. This is half wave plate at theta, and this is quarter wave plate again. Let me not write, maybe copy. And again quarter wave plate at 45 degree, and the light which is coming, that is vertically, let me not write this, and there is a polarizer. Polarizer making the light vertically polarized.
Excuse me, ma'am.
Yes. Yes, tell.
I have a question not related to polarization coherence but related to spatial coherence.
Yes, please ask. Yes, please ask.
What is what is spatial coherence area?
Spatial coherence area, that thing I calculated in previous class. So did you see the discussion session of previous week?
No, ma'am.
So you can visit that once. There I have explicitly calculated the coherence area by taking an example. Okay, so if you just visit that and check that, and if you have any problem, then you can write in that YouTube link, chat box, or maybe you can mail me. Is it fine with you?
Okay, ma'am.
And if you need any help regarding understanding that, then you can anyway mail me or ask a question, or whatever, in whatever manner you want to contact, you can contact me, I will help. But I have already discussed that in the previous discussion session. That's why I'm not discussing here in this discussion, in today's class. Okay. So okay, so first we have, suppose we have this scenario. I'm just giving you this scenario, that polarizer making the light vertically, some light is coming. There is a polarizer which is making the light vertically polarized light, then it is passing through one quarter wave plate, then it is passing through an half wave plate at theta degree, and then quarter wave plate at 45 degree. Now my question is, what will be the output? So for that, the points are: to use learn to write Jones matrix, and imply for the above case. Okay, so this is the homework. This is just to learn the polarization degree of freedom with with the help of matrix, and how to represent it, and how to do calcul. I mean, this is, maybe you are not understanding, but there are still this kind of work I mean, we actually do it, that we need to use quarter wave plate, half wave plate, and need to do the Jones calculus to understand what output we are getting if we do this, do that. Because and for, I mean, for to know those things, like, you need to learn by yourself that how I can represent each and every element in terms of matrix representation, and what will be the output. By that manner, you will get the idea which optical element had what kind of phase, and how to get output if you do not have any, how to understand that what will be the output if you do not have the idea of it. So first of all, we learned how to get the output electric field while we are using Mach Zehnder interferometer or Michelson interferometer, any kind of interferometer. Now I hope you can do now that thing for any kind of interferometer. And polarization is a bit different from those. And now you need to learn how to write electric field in case of polarization degree of freedom. So that's why this exercise will, this exercise will never come in exam, or any may also come, but hopefully it will not come. But you can to learn this, you can do this exercise by yourself. Sorry. So now we will discuss about coherent mode representation very quickly and go to the further problems. I will not write anything. I will just tell you, just to make you remember the things, as well as just to, like, such that if you have any query, or if you are finding anything difficulty here, then you can understand that. So a coherent mode representation is a can be done for a completely coherent field. If you have a coherent field, then you can, whatever you are doing, that is coherent mode representation. But what if you have partially coherent field? Then you can do coherent mode representation by coherent mode representation is a way of representing a partially coherent field as a mixture of coherent modes. What does that means is that partial coherent field is equal to mixture of coherent modes. If you take the help of angular, suppose, then you have some alpha L1 times EL1 corresponding to L1 orbital angular momentum, plus alpha L2 EL2, and plus so on. Then these are explicitly a coherent mode, and mixture of that, summation of them, what is what you give the incoherent mixture of it, which is a partial coherent field, and that's representation calls as coherent mode representation of optical field. I just gave you the example of orbital angular momentum field, I mean angle OM field, but you can do this for any basis. Okay, the motivation for finding this coherent mode representation is very easier to deal. Like if you have the idea of coherent modes, then the problems becomes very easy. And if a partially coherent field can be represented in terms of mixture of coherent modes, then one does not need to propagate the entire field. Rather, you can explicitly do the calculation for coherent field, and you can get the partial coherent field as a mixture of them. Okay, so it can be done for finite dimensional basis as well as infinite dimensional basis. Why I am talking about finite and infinite dimensional basis? Because I have already told you that the spatial degrees of freedom, temporal degree of freedom, angular or OM degree of freedom, these are infinite dimensional basis. Whereas this polarization degree of freedom is a two-dimensional basis, which is finite dimensional basis. And as I have also mentioned that this orbital angular momentum basis gives you discrete infinite dimensional basis, whereas the spatial or temporal degree of freedom, those provide you with continuous infinite dimensional basis. Okay, and as we are talking about basis, this always forms is always follows the rules of forming a complete basis, like the completeness theory and orthogonality, all of those, as well as the correlation functions are square integrable, they are Hermitian, and they are non-negative definite function. Okay, so these are always followed, like whatever the concept of quantum mechanics that we know for writing a particular state in in an invert space in a particular basis, then those things will be followed here also. There is no change in those. And the condition of hermiticity and non-negative definiteness conditions assures that the integral equation has at least one non-zero eigenvalue and all eigenvalues are real and non-negative. Okay, because eigenvalues, as it is Hermitian, you can understand that Hermitian gives you with the real eigenvalues. That's why in physical reality, anything that you require, we always find such kind of basis or such kind of uh, operator which are mostly Hermitian. Apart from that, we do not have any physical reality of those things. Okay, so here the concept of basis, whatever we follow in case of quantum mechanics, will be followed, and we will have similar things whatever we have done. We excuse me, yes, so we'll have the similar things whatever we used to follow in the quantum mechanics, basic rules of quantum mechanics. Okay, so the coherent mode representation is already explicitly done in the lectures, where you can understand the mathematical representation of it. Maybe it is finite dimensional polarization or infinite dimensional OM or spatial degrees of freedom. So I am not writing it in terms of mathematics again, rather we will solve the problem. But before going to the problems again, one more thing that you need to understand, that in classical mechanics, one straightway talks about a field, but in quantum mechanics we describe those in terms of state and operator. That you all have this idea, but still I am again recapitulating again it, such that you can do the transition now from classical mindset, classical things, and have the idea of quantum optics and quantum mechanical analogy of it. Okay, and the basic ingredients for quantum mechanics, you know that we represent it with psi, kate vector psi, and that we call a state. And a system in quantum mechanics is represented with the state vector. The system can be finite dimensional and even infinite dimensional. As long as a system can be completely described using a state vector, the system is said to be a pure state. So you need to understand now the concept of pure state and mixed state. So as long as a system can be completely described using a state vector, the system is said to be a pure state. However, when a quantum system cannot be described as consisting of a single pure state, it is said to be mixed state. Okay, and mixed state represented and any pure state representation again for a mixed state is non-symbolic. So like we can write it in symbolic manner, but it does not have any meaning. We should write it in terms of correlation. So just as in classical wave theory where we have coherent and partial coherent state, in quantum mechanics we have pure and mixed state. I hope you can understand. For a perfectly coherent field, we can say that perfectly coherent field is a pure state, whereas a partially coherent state is a mixed state, which we can write in terms of coherent mode representation. That means the sum of various pure modes or sum of various coherent modes. In terms of wave mechanics, we will call is at sum of coherent modes. In case of quantum mechanics, we'll say it as sum of pure modes. Okay, and the so we can do this kind of one to one correspondence, pure state and perfectly coherent mode, and this at mixed state as partially coherent mode. So these are the concepts that you need to now do the transition, because now we will study about the quantum mechanical perspective, all of these, and we will slowly go to the quantum entanglement. So these were the past 4 weeks where when you learned about the wave mechanics mostly, and what is coherent, incoherent, partial coherent, and how to deal in all of the degrees of freedom. Now it will be everything in the quantum mechanical in the quantum mechanical representation, like bracket notation, density matrix, and pure state, mixed state, operator, measurement, dynamics, Schrodinger picture, Heisenberg picture, all of these things. So I hope by the next class you will have a like you will recapitulate your quantum mechanics and remember it again. So for the pure state, we can for the pure state we can write the density matrix just like psi. This equals to this, because we can just remove the ensemble average, but for a mixed state we cannot do so. We need to write in terms of ensemble average always. Okay, because why? What does it mean by pure state? Pure state means if you have a psi, suppose at t1 you have something which is suppose psi 1 plus e to the power I delta psi 2. At t2 time you will have psi equal to psi 1 plus e to the power I delta psi 2, going on dot 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 dot. At tn times you will have psi equal to psi 1 plus e to the power I delta psi 2. That means over the time it has the same replicas, like these are the same things. Over the time there is no change in the field. Over the time it has the same state vector. That's why we can say it as pure state. And that's why when we take the ensemble average, and we can consider ensemble average as time average, and with the time there is no change in the state, so we can directly if we do psi ensemble average, we can directly write in terms of psi, because there is no change over the time. We do not need to take the time average, which is equivalent to the ensemble average for the stationary case. But if you have psi 1 plus e to the power I delta 1 psi 2, psi 1 plus e to the power I delta 2 psi 2 over the time. If it is varying and so on, then you cannot avoid the taking the time average. You need to take the time average, because over the time it is changing. You need to consider ensemble average. For stationary case it will become in time average, and you need to do this psi and its ensemble average for the mixed state. So this is the field of pure state and mixed state in and analogy with the coherent state, perfectly coherent state and partially coherent state. Okay, and now he will, from now on, for the quantum mechanical case, we will calculate the density matrix, because we know the density matrix is actually what gives us the information of total state. And if you do understand or do acquire the whole information of a density matrix, that thing is called quantum state tomography in scientific language, or in the research language. What is quantum state tomography? Like, if you have some state, and what you actually want to calculate is always density matrix, because you will operate. What does this means? This means you are taking some projection in a particular state, and whenever you do measurement, you can only calculate the density matrix, because you will take the projection. And if you have the density idea of the whole density matrix, then you can say each and every detail of the incoming field. And the process of finding all of the elements of density matrix is called quantum state tomography. And these are the current research field also. It is like maybe this is maybe hearing very easy, but to actually experimentally, theoretically, it is maybe easier than actually retrieve the whole information from any experiment practically. Okay, so this is the field of pure and mixed state, and analogy with the perfectly coherent state and partially coherent state. You also need to know about operator and measurement, because measurement is very important thing in quantum mechanics. And if you calculate like if a is an operator, and if you calculate the psi that is the expectation value of it, and do the ensemble average, then what you can get is trace of rho of a cap, where rho is the density matrix, and a is the operator. And if you take the if you find the trace of it, then you will get the measurement. Okay, and for the dynamics, you can use the Schrodinger equation, h psi I h bar del psi del t. Okay, this is the Schrodinger equation. So these things I am just telling you, just to remember or recapitulate all of the things that you have learned in your quantum mechanics, and to make an analogy one to one with the wave mechanics, whatever we have learned in the past 4 weeks and what we are going to learn in the next 8 weeks. Okay, and this 5th week is the transition period. So after all of this discussion, let us solve few problems related to your assignments, and as well as to mostly I will solve for the special degree of freedom, 2 special degree of freedom and 1 OM basis. The thing is that what I can tell, like what we discuss in terms of theory, that mostly what we learned in that week and what I do in case of problem solving, those are in comparison with the assignments, that is lagging behind, that is mostly slightly lagged behind the uh, theoretical lectures or theoretical part. So this is your question for today. Let us take a 2 minute 1 minute break, and then we'll start it. Okay, so the problem is saying the far field Van Sitter-Jarnicke theorem is given by W rho 1 rho 2 z equal to k0 by 2 pi z, whatever it is given as equation 2. Here W rho 1 dash rho 2 dash z equal to 0 and W rho 1 rho 2 z are the cross spectral density function of the field at the source and in the far field. This rho 1 dash rho 2 dash z equal to 0 is at the source, and this rho 1 rho 2 z is at far field, which is after using the Van Sitter-Jarnicke theorem. Alright. Now also k0 equal to k equal to 2 pi by lambda 0, where lambda 0 is the wavelength of the source, and now consider the sun to be a spatially completely incoherent source in the form of a uniformly illuminated disk of radius r equal to 7 into 10 to the power 8 meter. Take the distance between the sun and earth to be 15 into 10 to the power 10 meter and lambda 0 equal to 600 nanometer. Work out an order of magnitude estimate of the coherence area of sunlight on the earth. Oh, somebody was here just few time before. Who was asking the question? I think she is not here. Bhairavi or someone. She just went away. So maybe otherwise she will have a chance to understand what is coherence area and at this moment also. So all right, just let me discuss here, and I will ping her sometimes maybe. So the question it is saying is that everything is given to you and you need to calculate the coherence area of sunlight on the earth, and everything else is given, and it is mentioned that sun is a spatially completely incoherent source with uniform intensity. So we can write W rho 1 rho 2 Z equal to rho 1 rho 2 Z equal to A delta rho 1 dash minus rho 2 dash. This is in source plane, and this is in earth, earth plane, or like after propagation, the object after propagating a while, this is the far field. Okay, so for that reason, whatever equation we have as equation 2, now we can write that in this manner. One minute. Delta rho 1. One minute. Okay, I just solved it before some time, before starting this class. So I myself had made some mistake. So the thing it will be this is not the far field. Like, what equation we have is W rho 1 rho 2 z in terms of W rho 1 dash rho 2 dash z equal to 0, and it is told to you that It is specially completely incoherent at source plane. Source, like completely incoherent source, that means it is incoherent at source plane. That means at w rho 1 rho 2 rho 1 dash rho 2 dash at z equal to 0, we can write it in terms of a delta rho 1 dash rho 2 dash, because we know that for a completely incoherent source we can write it in terms of Dirac delta, that we have already seen in various cases. Why Dirac delta? Because if it is rho 1 dash equal to rho 2 dash, then only it will be a, otherwise for as it is incoherent, for that reason there is no correlation between other. So if rho 1 and rho 2 are different, then it will be 0. Okay, so this is known to us. Now we want to find out w rho 1 rho 2 at z, that means far field. So we will substitute this w rho 1 dash rho 2 dash z equal to 0 in this equation, which will give us 2 pi z e to the power I k 0 rho 2 square minus rho 1 square by 2z integration w rho 1 dash rho 2 dash z equal to 0 to the power minus I k 0 by z rho 2 minus rho 2 dash rho 1 dash d rho 1 dash d rho 2 dash. Okay, so this thing you need to calculate, and I hope you can understand that this question is already given to your some assignment, I think so. So this is what the various options are given, but I do not need, I should not tell about the problems and the solutions, so I will not I don't want to actually discuss, but I just want to show you the glimpse that maybe some of the discussion session you will be able to get some of the questions from your assignments and end semester. So the now you need to, what you need to do is to solve solve this, and for that first you need to substitute this a, first you need to substitute this, and it will become e to the power minus I k 0 by z rho 2 minus rho 1 dot rho and d rho. Okay, where rho is the xy. Now this above integral gives Bessel function, or I do not need to even tell you. If you calculate it in every step, then you will be able to solve the integral. Maybe let me write it one more step, one or two more step, then you will be understanding. So this is this it is about I k 0 x2 square plus y2 square minus x1 square plus y1 square by 2z minus r2r e to the power minus I k 0 by z delta x dx minus r2r e to the power minus I k 0 delta y by z dy. So you have two integrations in Cartesian coordinate, just simple e to the power minus integration. Oh, one more thing, why I am writing minus r to r, because it is already given the radius of the sun is already provided with you, and we can approximate this sun as a circular disk of radius r, and the diameter is 2r. So if we consider the center, from center it is minus r to r that we need to integrate in x and in y. Although it is although it is a circular disk, but as it is far away from us, so we can consider it as flat space or square disk also, because the circularity will not much matter here, because it is far away from us. I think I mean, you can understand that if it is close to us, then we need to consider the structure very well. But if it is far away from us, then we do not need to worry about the what is the structure of it that much. So based on these, you just need to solve this integral now, and it will just become sinc function. So a k0 2 pi z, and of course delta x is x2 minus x1. I have already calculated the steps beforehand, that's why I can write it so smoothly. Otherwise it requires practice and it requires so many steps to solve. So don't worry about that. I have already solved it by myself, and solving and showing you the solutions, how to solve it. So x2 minus x1 equal to del x, and y2 minus y1 equal to del y, and a k0 by 2 pi z e to the power I k0 x2 square plus y2 square minus x1 square plus y1 square by 2z, and if you integrate, then you will get 2r sinc k0 r delta xz sinc k0 r delta y by z. Now I have mentioned previous class also, this class again I am mentioning, the first zero of the sinc function can be used for estimating the spatial coherence length, and first zero of sinc function means k0 r k0 r delta x by z will be equal to pi. Therefore, the spatial coherence length of the sunlight on Earth for this case will become how? Because I have already mentioned, this is the condition. Why? First zero of the sinc function can be used for estimating the spatial coherence length. And this will become del x equal to pi z by k0 r. Pi z means the distance between Earth and Sun. K0 means 2 pi by lambda, which is lambda is 600 in 10 to the minus 9. We are considering on an average red light mostly. 7 into 10 to the power 8, and it will become approximately 64 micrometer. This is the spatial coherence length, and coherence area will become nothing but 64 micrometer square, which is 4096 micrometer square. Okay. So this is how you need to calculate. Now the problem 3, next problem. This is also your assignment problem. So I will just show you A and B part. C and D part, it is already your assignment problem, so you need to do it by yourself. I will not I'll not solve you because otherwise I cannot provide you with the assignment solution. And I wanted to discuss one more question, but maybe not today if the time does not permit, because now we will directly solve the problems of angular degree of freedom and polarization degree of freedom. All right, so the next question, it is saying consider a one dimensional spatially completely coherent field Vx z equal to 0 at this plane, which is A, and passing through a phase screen. That means this screen is adding some phi x phase of negligible thickness kept at z equal to 0. The screen imparts a phase to the field. Calculate the cross spectral density function and the degree of coherence function right after the phase screen. Now you need to calculate this cross spectral density and the degree of coherence function after the phase screen for different condition. I will show you for the first two condition, and after that you can find out by yourself that how others you can do. So in this case, right after the phase screen, we have Px z equal to 0 equal to a to the power I phi 0. That means w x1 x2 z equal to 0 will become v star x1 z equal to 0 v x2 z equal to 0, which is equal to a square, and mu x1 x2 z equal to 0 equal to w x1 x2 z equal to 0 by root over of w x1 x1 z equal to 0, that means the intensity I x1 x1, and w x2 x2 z equal to 0, that means I x2 x2. If you calculate it, then it will become a square by a square, which is equal to 1 for the first case, where phi 0 is constant. Now the second case, where it is saying phi is now f0x, that means it is a function of x. That means based on like what you will learn from this problem is that based on different phases, you can actually have different cross spectral density and coherence, degree of coherence function. Maybe degree of coherence can that will also vary, that you will see eventually, but w is very much sensitive to this phase. As w is sensitive, mu is also sensitive, but mu is normalized version of it. But cross spectral density is directly what we have the information from everything environment. We have the light is passing, the electric field is passing from whatever the things there is present there. So for that, measuring cross spectral density is what actually the main challenging aspect, and that gives all the information about the field. Okay, so this was the part A, like where we calculated the phase screen Vx, and that will become a to the power I phi 0 at it mentioned that phi 0 is a constant and phi x equal to phi 0, and we calculated w, we calculated mu, which becomes 1. Now for the case B, we'll do so Vx z equal to 0, a e to the power I f0 x, w x1 x2 z equal to 0, v star x1 z equal to 0, v x2 z equal to 0 equal to a square to the power minus I f0 x1 minus f0 x2. Okay, because now it is a function of x and x1 and x2, and function of x position, so we cannot remove them. So this is the w, and mu will become w x1 x2 z equal to 0 by w x1 x1 z equal to 0 into w x2 x2 z equal to 0 equal to 1. So this is the degree of coherence. And the next part, it is saying when the phase screen is such that it changes randomly in a continuous manner with phase kx. Here k is a random variable with probability density pk is like this. Then what will be the cross spectral density and degree of coherence? And part D is saying for the last part, calculate the spatial coherence length of the field right of the phase screen. So these two part I am giving you as homework again, because not homework, these C is in assignment or quiz. C is in quiz, and D I forgot if it is in quiz or not, but homework. So I hope you can understand that the discussion sessions are very important to those mainly who are going to write the end semester examination. So this was all. Today I will end maybe a little faster, not take much time, and as it is, I have already given you the homework and whatever I wanted to do. This is just the problem 4. I will mention once, not solve today. I'll start the next week by solving this problem. 3, I'll solve the C and D part of this problem 3, and then I will solve this problem 4. And by discussing these two things, I'll start next discussion session. So it is just saying that consider an optical field V phi, that is coherent superposition of modes carrying OM index L and minus L. V phi equal to e to the power IL phi plus e to the power minus IL phi. What is the azimuthal correlation function, and what is the corresponding azimuthal intensity S phi? I am very sure that you will get this question in your quiz. So try to understand and solve this problem in whatever manner what we did it for the temporal case and spatial case. It will just be same like this, but now it is in different degree of freedom, which is angle OM degree of freedom. So try to do it by yourself. I am giving it to you. You will have this question in assignment for sure, and this kind of question you will get in your end semester examination also. So this is also your homework problem, like not homework, like just have a look and try it by yourself, and then we'll discuss in the next class. So this is all for today's discussion session, and now I will just formally wrap up today's discussion. As I always mention that this was week 5 degree discussion, and the things whatever I am writing here in my writing iPad, and whatever the slides are, that will be uploaded in that will be updated in the drive folder, and you have the access of the drive folder through the SWAM portal. And I have also shared the drive folder with you. And for anything, if you have missed this class discussion session, you can get these discussions in YouTube channel, my YouTube channel link, and that is also shared with you. And if you have, then it's fine. So there you visit for this uploaded videos, and of course do go through the lectures and this discussion session. It will help you to get good marks. So by saying this, if you have anything to discuss or ask, then you can say it, or otherwise I will wrap up today's discussion session. So do you have anything to say? Okay, all right. If not, then I will say goodbye to you, and let me stop today's discussion session. So bye bye.